Morning, I am Assistant Professor Rajesh Kocheri from Tokach Institute of Science and Technology. My field of specialization is thermal engineering. I am going to take a class on Otto Cycle, its PV diagram, TS diagram, efficiency derivation, and a numerical. This subject is for the second year, that's for the fourth semester. The main objective of this topic for a mechanical engineering student is that you should be aware of how especially the IC engine works, because most of us use either a two-wheeler or a four-wheeler for our conveyance, and we should know the basics of an engine so that at least we are able to perform or able to do the first line maintenance, and also we are aware how the engines which is fitted on a motorcycle works. The main content of this presentation is the PV and the TS diagram of Otto cycle. Otto cycle is a constant oleum cycle. Constant oleum cycle means the heat addition takes place at constant oleum and heat rejection also at constant oleum. And the efficiency derivation of Otto cycle followed by a numerical on Otto cycle. The main process involved in a Otto cycle, we can say, let us take a small petrol engine. There are 4 different processes involved in it. This process you can be analogous to the digestive system of a human body, where we open our mouth and feed food into it. It's something similar in an engine too, where the inlet valve of the engine opens and the food for the engine is air and fuel. So in a small petrol engine, it's a homogeneous mixture of air and fuel enters into the cylinder, same as the way we feed food into our mouth. Then subsequently, once we feed food into our mouth, we close it. Same way, once the air and fuel is being taken in, subsequently the inlet valve of the engine is closed. In this process, when we are about to start the inlet stroke, the piston is at TDC, that is the top dead center. That means it's at the topmost part of its reciprocation, and subsequently the piston moves down. When piston moves down, that time there is a difference of pressure delta P. The atmospheric pressure will be higher than that of the pressure inside the cylinder, because when the piston moves down, it acts like a vacuum pump. So because of the difference of pressure, air from the atmosphere moves in, and when the cylinder is filled with the charge, its inlet valve is closed. Then after we feed food into our mouth, we close it. Then subsequently it passes through the intestine. The food the volume of the food is reduced. Subsequently, the temperature of the food increases. Same in the engine, when the piston moves from the bottom dead center to the top dead center, the volume is reduced, and subsequently work is being done on the fluid. Here the fluid is air and fuel. It's a mixture, it's a homogeneous mixture of air and fuel. As the piston moves up, the temperature and pressure increases as the volume is reduced. This time both inlet and exhaust valve is closed. Then subsequently, when the piston is about to reach the top dead center, that time the spark plug which is provided into the cylinder will initiate a source of spark, and subsequently this spark propagate into the mixer and ignite it. We should understand one thing, that in a cylinder the combustion is not a fire, because the resultant of fire is heat, light and sound. Therefore, if explosion takes place inside the cylinder, then the resultant will be the heat, light and sound. Maybe you and me may not be able to stand in a traffic place where a lot of vehicles be idle and their engines are working, because the resultant noise will be so high. Therefore, in an engine it is a propagatory burning, which we call as combustion. Then subsequently, when the homogeneous air and fuel mixture is burned, the chemical energy is converted into heat energy, and this heat energy does a work on the piston, and subsequently it's converted into mechanical energy and onto the wheels. When the piston moves down, the volume is increased, and subsequently the temperature and pressure inside the cylinder also reduces. And when the piston reaches bottom dead center, that time the exhaust valve is opened and the flue gases which is remaining inside the cylinder will start moving out. In actual cycles, this valve opens some degree before BDC, so that, and this time the inlet valve is opened because after the exhaust stroke, the next process is inlet stroke. Now, during this period, the air-fuel mixture which is there passing through the inlet valve is denser than the hot flue gas which is there inside the cylinder. So, this denser air or air-fuel mixture will push the hot gas to move through the exhaust valve, additionally with the movement of the piston from BDC to TDC. And this will ensure that proper scavenging is being taken place and ensuring that the hot flue gas is out of the cylinder. If this hot flue gas remains inside the cylinder, then subsequently that will get mixed with the incoming fresh charge, and subsequently the charge get contaminated, and the amount of air available in the combustion process reduces. Subsequently, you can say that the efficiency also reduces. Now, based on this process, the Otto cycle works. Now, in this process, the 0 to 1, in this the process, the 0 to 1 is actually the section stroke. And in this stroke, the inlet valve is open, air is being taken in, and from point 1 to 2, we can say that point 1 to 2 is the adiabatic compression. Adiabatic compression means the piston moves from BDC to TDC and the volume is reduced, and this is adiabatic compression is process 1 to 2. And in this process, the volume is reduced, and subsequently when it reaches point 2, the heat is being added, and in this case it is added in the form of a spark plug. It is being added. So point 2 to 3 is heat addition, and this heat addition
takes place at constant volume.
When the spark is initiated at point 2, that time the charge get ignited. Charge means the air fuel mixer get ignited, and subsequently there will be a steep hike in the pressure till point 3. And when the piston starts moving down,
when the piston moves from TDC to BDC, that time the volume is increased and subsequently the temperature and pressure of the charge is reduced. So during the expansion process, when the volume is increased, when the piston moves from TDC to BDC, that time the temperature and pressure of the charge subsequently reduced. The temperature and pressure of the charge subsequently reduced.
Where the heat is being rejected, that is from point 4 to point 1, the heat rejection take place, and subsequently 1 to 0, or you can say 1 to 6 is the exhaust stroke. This is how the process takes place in an Otto cycle. Now let us see the PV diagram and TS diagram, pressure volume diagram, and the temperature entropy diagram of Otto cycle. As I said, the process 1 when it is at point 1, the cylinder is fully charged with air fuel mixture, and 1 to 2 is the compression. So the volume is being reduced, there is a change in volume, and we can call this volume from point 1 to point 2 as the clearance volume, because the clearance volume Bs, the swept volume, the volume swept volume Bs is the volume swept by the piston from one dead center to the another dead center, that is either from the TDC to BDC or from BDC to TDC. In this case, the piston moves from BDC to TDC, therefore a reduction in volume, and this volume from 1 to 2 is what the swept volume Bs, and the volume above the piston when the piston is at TDC is clearance volume, and we call it as V2 or VC. Then 2 to 3 process is heat addition takes place, QAN, and 3 to 4 is the adiabatic, reversible adiabatic or isentropic expansion, and 4 to 1 is heat rejection. Now let us see the temperature entropy diagram of Otto cycle. The heat addition takes place at this particular point where the temperature increases from point 1 to 2, and subsequently from 2 to 3 you can say that the heat is being added into the system, and the system absorb, or you can say the charge absorb heat from the source, and here the source is spark plug, and subsequently from 3 to 4 is actually the work done. Work done takes place at 3 to 4, and 4 to 1 is subsequently the heat rejection. Therefore, we can say that the entropy at point 1 and the entropy at point 2 is same, and the entropy at point 3 will be similar to or same as that of entropy at point 4. Then the same process for easy understanding, 1 to 2 is inlet, 2 to 3 is compression stroke, 3 to 4 is combustion, you can say, and 4 to 5 is your expansion or power, and 5 to 6 is heat rejection. Now same, this is what I said, the process 1, the inlet valve is now open, air from the atmosphere is being taken in. As the piston moves down this much volume, if let us say this is the bottom dead center and this is the top dead center, so the volume swept by the piston from TDC to BDC is the clearance volume. And when the piston, now in this case the piston is at TDC, and the volume above the piston we call it as the clearance volume BC, or you can call it as V2. Now after this section process, as the piston moves up, you can see the both inlet and exhaust valves are closed, so the charge is being compressed, and when this piston exert a work on this fluid, subsequently the temperature and pressure increases. And then when it is about to reach the TDC, the spark is being initiated and the charge inside ignites in a propagatory way, maybe something similar to the waves. Then subsequently the power, the explosion or the power generated acts on the piston, and subsequently the piston moves down, and through the connecting rod the piston is connected to the crankshaft, and at the end of the crankshaft through different power transmission arrangements, it is either transmitted to the wheels or to the diesel alternator, or maybe to the propeller if it is in a case of a ship or maybe in a motorboat. And thereafter the exhaust valve is open, and when the piston moves up, the hot gas remains inside the cylinder will be pushed out through the exhaust valve through the silencer to the atmosphere, and meantime the inlet valve also is open. Now this Otto cycle is an idealized thermodynamic cycle which tells you exactly how a spark ignition engine works. Generally we classify the engines are spark ignition engine and compression ignition engine. The basic difference between these two is that in a spark ignition engine you give a source of spark to the charge using a spark plug, whereas in compression ignition engine there is no spark plug. The air fuel mixer get ignited by automatic ignition, or you can say by the spontaneous ignition. There is no additional source of spark given into the charge. And Otto cycle provides what happens to the mass of gas when it is subjected to changes of pressure, temperature, volume and addition of heat and removal of heat. So we discussed this because there is a change in pressure, there is a change in temperature, there is a change in volume, then you add heat and then you remove the heat from the system. The mass of gas that is subjected to these changes is termed as a system, and in this case our system is the fluid, or you can say the homogeneous mixture, that is the air and fuel which is inside the cylinder when piston moves from the TDC to BDC. Then Otto cycle is constructed in this, which we already discussed. Otto cycle is constructed in such a way that if you measure the volume of 1 to 2 and 3 to 4, it is same. So you can say that the volume swept from 1 to 2 and volume swept from 3 to 4 is same. And the construction of this PV diagram is in such a way that the left and right side of the loop is a pair of parallel constant volume process, that is process 2 to 3 and process 4 to 1 or 4 to 1. This is the heat addition takes place at constant volume, whereas 4 to 1 is heat rejection takes place at constant volume. So in this case you can say that V1, the volume at 1 and the volume at 4 are same, so V1 is equal to V4 and V2 is equal to V3. These terminologies are required when we do the numerical on Otto cycle. And process 1 to 2 is isentropic, reversible, adiabatic. Process 2 through 3 is constant volume heat addition, and process 3 to 4 is reversible, adiabatic or isentropic expansion, or you can say it's a power stroke, and 4 to 1 is heat rejection at constant volume, and 1 to 0 is the inlet stroke. So to conclude this, let us say that the Otto cycle consists of isentropic compression, heat addition at constant volume, isentropic expansion and heat rejection at constant volume. Now let us get into the derivation, how to derive or to get into the efficiency or to find out the efficiency of Otto cycle. We generally denote the efficiency in terms of eta, and efficiency is in any process, it is the work done by the heat supplied. In case of an IC engine, internal combustion engine, you can say the efficiency is the work done divided by the total heat supplied to the system. Now let us consider 1 kilogram of substance. Here the heat supplied at constant volume, we call the heat is being supplied either at constant volume or at constant pressure. If the heat is supplied at constant volume, we call it as CV, and if the heat is being supplied at constant pressure, we call it as CP. Here the heat addition and heat rejection takes place at constant volume. Therefore, the heat supplied is CV into T3 minus T2. Why T3 minus T2 is, this is the point where the heat addition is cut off, and T2 is the point where the heat addition commences. Therefore, we can say that the heat supplied to the system is CV is constant at constant volume, T3 minus T2. And heat rejection, as you are aware that it is from the process 4 to 1. Therefore, the heat rejection at constant volume is CV into T4 minus T1. Now we can say that the work done is heat supplied minus heat rejected. In an IC engine, the heat work done is heat supplied minus heat rejected. Heat supplied is CV into T3 minus T2 and heat rejected is CV into T4 minus T1. Therefore, we can say that work done in an Otto cycle is CV into T3 minus T2 minus CV into T4 minus T1. Now, the efficiency of the cycle is work done by heat supplied, and work done is heat supplied minus heat rejected. Therefore, efficiency eta is heat supplied minus heat rejected by heat supplied. As you are aware that heat supplied is CV into T3 minus T2 and heat rejected is CV into T4 minus T1. This divided by the heat supplied CV into T4 minus T1 will give you the efficiency of the cycle if you know the temperature at all salient points. And the salient points are T1, T2, T3 and T4. So, and the value of CV is known to you, and it is fixed. The value of CV is 0.0718 and value of CP is 1.01, and Cp by Cv is your gamma, and that is 1.01 divided by 0.718 gives you 1.4. This particular value we should keep in mind for the numerical because it may not be given most of the time. Therefore, the value of gamma for air, this is only for air, gamma for air is 1.4 and there is no specific unit for it, and gamma is Cp by Cv. Therefore, the efficiency becomes, when we consolidate this, we get the efficiency as 1 minus T4 minus T1 divided by T3 minus T2. And we are aware that the compression ratio is the total oleum in a cylinder divided by the clearance volume. And the total oleum is the oleum swept by the piston Vs plus the oleum above the piston when the piston is at TDC beneath the cylinder head. That means the oleum between the piston and piston crown and the cylinder head bottom part when the piston is at TDC is what clearance volume is. We can call this volume as bumping clearance also. So the compression ratio is the total volume, that is Vs plus Vc divided by the clearance volume Vc. And as you are aware that for the numerical, we take Vs plus Vc as V1 and Vc as V2. Therefore, compression ratio in some textbook it is denoted as simple R, and in some textbook it is denoted as RC. So R, whether it is R or RC, it is V1 by V2. And the expansion ratio, you know that the expansion takes place from process 3 to 4. Okay, and we can call this ratio, expansion ratio, as RE. And this ratio is the oleum at V4 divided by the oleum at V3. So expansion ratio RE is V4 by V3. Now, as I discussed, Cp by Cv is gamma, and gamma for air is 1.4. In Otto cycle, two ratios are the same, that is the temperature and the oleum. Now, therefore, for numerical, doing the numerical, we can say that the T2 by T1, that's the temperature at the point 2 divided by the temperature at point 1, T2 by T1 is the V1 by V2 raised to gamma minus 1, and the value of gamma is known to us, it is 1.4. Now, from this T2 by T1 is equal to V1 by V2 gamma minus 1, we can find out what is the value of T2. Therefore, maybe in the numerical session you may give the value, you may have the value of T1, the temperature at salient point 1, you may not have the value of T2. But if you know the oleum V1 and V2, you can find out the value of T2 because value of gamma is known to you. Now T2 is, from this equation you can find out T2 is equal to T1 into R raised to gamma minus 1. Why R raised to gamma minus 1 is because R is V1 by V2. Or you can say T1 into V1 by V2 raised to gamma minus 1. Whereas V1 by V2 is R. So in simple terms, if you know the value of compression ratio and temperature at salient point 1, you can find out the temperature at 2, salient point 2. Similarly, T3 by T4 is equal to V4 by V3 raised to gamma minus 1. Now, if you know the temperature at one point, then you can find out the temperature at the next point also in this expansion case. So, T3 is equal to T4 into R raised to gamma minus 1 because V4 by V3 is same as V1 by V2. As we already discussed, the oleum is same at this point. Therefore, we can say that T3 is equal to T4 into R raised to gamma minus 1. Now, by substituting these values into the efficiency of Otto cycle, as the efficiency we have described in terms of temperature earlier, and now if we substitute the values into the temperature terms, we get 1 minus T4 minus T1 divided by T4 into R raised to gamma minus 1 minus T1 into R raised to gamma minus 1, and that is equal to 1 minus T4 minus T1 divided by R raised to gamma minus 1 into T4 minus T1, because here it is T4 into R raised to gamma minus 1 minus T1 into R raised to gamma minus 1. Now taking this out, R raised to gamma minus 1, we can write this equation as T4 minus T1 by R raised to gamma minus 1 into T4 minus T1. Now solving this into and simplifying this, you can write as T4 at minus T1 is there both in the here. You can simplify this into 1 minus 1 by r raised to gamma minus 1. Therefore, from this you can find out the efficiency of an Otto cycle if you know only one value, that is the compression ratio R. So the efficiency of Otto cycle can be obtained if you know either the temperature at all salient points in terms of temperature, or if you know the compression ratio airflow alone. So efficiency of Otto cycle is 1 minus 1 by r raised to gamma minus 1. Now in this I would like to conclude into a session where I wish to tell you that the efficiency totally depends upon the compression ratio. As you are aware that the efficiency will increase if there is a change in the compression ratio. Okay, so the efficiency of Otto cycle totally depends upon compression ratio. The only factor or the prime factor that affect the efficiency of Otto cycle is its compression ratio.
Now we are going to do a numerical on Otto cycle. As you are aware that Otto cycle is a constant Oleum process. So heat addition and heat rejection takes place. Keep in mind that heat addition and heat rejection takes place at constant Oleum. And the Oleum at 0.2 to 0.1 and 0.3 to 0.4 are same. So V1 will be equal to V4, V2 will be equal to V3. Now keeping this in mind, now we are going to do a numerical. And the question is, the minimum temperature and pressure in an Otto cycle are 27 degrees Celsius and 100 kilopascal. The amount of heat added to the air per cycle is 1500 kilojoules per kilogram. Determine the pressure and temperature at all points of air standard Otto cycle. B. Calculate the specific work and thermal efficiency of the cycle for a compression ratio 8:1. Take for air CV equal to 0.72 kilojoules per kilogram Kelvin and gamma equal to 1.4. Now before you get into solving this numerical, you should keep in mind how a PV diagram of Otto cycle looks like. So you should draw the PV diagram of Otto cycle before you actually proceed for doing the numerical, and mark whatever values are given in the PV diagram itself, so that at the end when you finish you are aware that all questions are answered appropriately. Now PV diagram is, I have drawn the PV diagram in the board, and the salient points are 1, 2, 3 and 4. That means you need to find out the temperature at 0.1, 0.2, 0.3, 0.4 and pressure at 0.1, 0.2, 0.3 and 0.4. Now in the question, in the given data are at 0.1 the pressure is given as 100 kilopascal. So you can mark that in the PV diagram at 0.1, 100 kilopascal. And the temperature is also given 27 degrees Celsius. Keep in mind you will have to convert this into Kelvin. Therefore 27 plus 273 is 300 Kelvin. Mark in the PV diagram itself. Then rest of the values you have in the question is heat supplied is 1500 kilojoules per kilogram. That means heat supplied is CV into T3 minus T2. So you can say that CV into T3 minus T2 is 1500 kilojoules per kilogram. The compression ratio is 8:1. And compression ratio you are aware it is V1 by V2, or you can say it is total oleum by the clearance oleum, or you can say it is Vs plus Vc by Vc. So that value is given as 8:1. Then the Cv is given as, this is a constant oleum process, Cv is given as 0.72 kilojoules per kilogram Kelvin, and gamma, that is Cp by Cv, is 1.4. Now keep in mind that it is not mandatory that the value of Cv and gamma is given in all the questions. You should by heart this, you should know this, the value of Cv, Cp and gamma, and Cp by Cv is gamma, that is 1.4. Now let us take each process, that is the first point is at point 1, already the temperature and pressure is given. Now let us take process 1 to 2. Now in the derivation itself we know that we are aware how to find out the temperature at this particular point T2, and if you know the T1 then you can easily find out the values at T2. And process 1 to 2, T2 by T1 is equal to V1 by V2 raised to gamma minus 1, and you are aware that V1 by V2 is compression ratio R, and in the question compression ratio R is already given. Therefore, now T1 is known to you, V1 by V2 raised to gamma minus 1, V1 by V2 is compression ratio R, which is known to you, value of gamma is known to you, therefore you can find out T2. Then substituting the values, you get V1 by V2 raised to gamma minus 1 is R raised to gamma minus 1, R is 8 in the question, so 8 raised to 1.4 minus 1, that is 8 raised to 0.4. The value is 2.297. Okay, so 2.297 is the value of T2 by T1. Now T1 is known to you, so therefore T2 is equal to T1 into this 2.297, and that gives you T1 into R raised to gamma minus 1, R raised to gamma minus 1 is 2.297. So you get the value of T2 as 689.1 Kelvin, that you mark in the PV diagram. So T1 is marked, P1 is marked, now T2 is marked. Now we need to find out P2. Now in the Otto cycle, in this process, V1 raised to gamma, P1, pressure at this point 1 and volume at point 1 is equal to P2 V2 raised to gamma. So P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Now if you have P1 and V1, then you can easily find out P2. So P1 V1 raised to gamma is P2 V2 raised to gamma. So P2 by P1 is equal to V1 by V2 raised to gamma. And you are aware that V1 by V2 is compression ratio R. Therefore, P2 by P1 is equal to R raised to gamma. That is 8 raised to 1.4, 18.37. So P2 by P1 is equal to 18.37. Now P2 is P1 into 18.379, and in the question P1 is given as 100 kilopascal. So that is 1 into 18.379, and you get the same value, 18.379. Therefore, at P2 the pressure is 18.379. Now we have already found out what is the temperature and pressure at point 2. Now let us see the process 2 to 3. So process 2 to 3 is heat addition at constant oleum. So the oleum here is constant and the pressure is increasing. And at point 2 the temperature is 689.1 and the pressure is 18.379 bar. Now as you are aware that in the question itself it is given the heat supplied is 1500 kilojoules per kilogram. That means from point 2 to point 3 the heat supplied is 1500 kilojoules per kilogram. And in the derivation we have, we know that the heat addition is Cv into T3 minus T2. As the process is constant oleum, it is Cv. So Cv into T3 minus T2. Therefore, Cv into T3 minus T2 is 1500. And the value of Cv is known to us, T2 is known to us. Now we can find out T3. So 0.72 into T3 minus 689.1 is 1500. Now when we substitute the values, T3 will be 1500 divided by 0.72 plus 689.1. So the value is 2772 Kelvin. So the temperature at point 3 is 2772 Kelvin. Okay, so from 689.1, when we supplied heat to that, the temperature has increased to 2297 Kelvin. And you are aware that when the temperature is increased, as the oleum is reduced, the pressure will also increase. Now let us find out what is the pressure at this particular point 3. Now P2 by T2, that is P2 by T2, temperature at this point and the pressure P2 by T2 will be equal to P3 by T3. Because the temperature and pressure increases correspondingly, so P2 by T2 will be equal to P3 by T3. So you can, so now when you substitute the values, you can get the temperature at point 3, that's T3 will be 1500 divided by 0.72 plus 689.1. That gives you the value of 2772 Kelvin. So the temperature at point 3 is now known to you. You can watch that from 689.1, when you substitute or when you add heat into this, the temperature has increased to 2297 Kelvin. Now, as you are aware that the temperature has increased and the volume is reducing, the pressure should also be increased. Now, let us find out what is the pressure at the point 3. Now, P2 by T2 will be equal to P3 by T3. As the temperature and pressure increase correspondingly, P2 by T2 will be equal to P3 by T3. Now, when you cross multiply, you can find out what is the value of P3. P3 will be equal to P2 into T3 by T2. And now P2 is known to you, T3 is known to you, T2 is known to you. When you substitute the values, you directly get P3. That the P3 will be the value of P2 into T3 divided by T2. That gives you 73.94 bar. So the pressure from 18.379, it is increased to 73.94. Now the point left with us is at point 4, what will be the temperature and pressure. Now process 3 to 4, you are aware that it is expansion. So definitely the volume will be increased and subsequently the pressure and temperature should reduce. Now you should, when you mark these points and when you find out the values, you should have a basic idea at the point 1, what will be the temperature that will be higher at point 2 and the maximum will be at point 3. Okay, and at point 4 will be the second highest value because heat is being rejected at this particular point. Now let us take process 3 to 4, the expansion process, and in this you know that T3 by T4 as T2 by T1 is V2 by V1, same T3 by T4 will be equal to V4 by V3 raised to gamma minus 1. And V4 by V3 is equal to V2 by V1. So V2 by V1 is, V1 by V2 is R. Therefore, V3 by V4 will be R. So you can write now this T3 by T4 is equal to V4 by V3 raised to gamma minus 1, that is R raised to gamma minus 1, and the value of R is already known to you. We have found out this particular term earlier. Now put that value as 2.297. Now T4 will be T3 divided by 2.297 and value of T3 is 2772.4 and value of R is 2.297. You get the value as 1206.9 Kelvin. So the temperature at point 4 after expansion will be 1206.9 Kelvin. From 2297 Kelvin, when expansion takes place, the temperature has been reduced to 1206.9 Kelvin. And you should know that the pressure at this point will also be lesser than the pressure at point 3. Now let us find out what is the pressure at point 4. As we are aware, P1 V1 raised to gamma, P1 V1 raised to gamma is P2 V2 raised to gamma. So P3 V3 raised to gamma is P4 V4 raised to gamma. Now when we substitute this, P4 is equal to P3 into V3 by V4 raised to gamma. And V3 by V4, you are aware that it is V2 by V1. V2 by V1 same, that is R, that becomes R. Now put the value, P4 will be equal to, the value of P3 is 73.94 and then 1 by 8, 8 is the compression ratio, and raised to gamma 1.4, you get 4.023 bar. Now at this 0.4, the pressure is 4.023. Okay. And now all temperature and pressure at the salient points is being already calculated and noted. Now we have already found out the temperature and pressure at all salient points. Now the next part we need to find out is the specific work and thermal efficiency. And as you are aware that specific work W is equal to specific work is equal to heat supplied minus heat rejected. And heat supplied is CV into T3 minus T2, and heat rejected is CV into T4 minus T1. Now you have the values of all this with you. You know the values of T3, T1, T2, T3 and T4 and CV. Now when you substitute the values, you get the specific work as 847 kilojoules per kilogram. Now the last part of this numerical is to find out the thermal efficiency of the cycle. And thermal efficiency, as we already discussed in the derivation, that the thermal efficiency depends mainly on the compression ratio R. And the equation for finding out the efficiency of Otto cycle is 1 minus 1 by R raised to gamma minus 1. And the only part which you need to put the value is the compression ratio R and the gamma, rest all is 1. So 1 minus 1 by 8 raised to 1.4 minus 1, that becomes 0.4. So 1 minus 1 by 8 raised to 0.4 is 0.5647. Now you'll have to put this in the percentage, so into 100, the efficiency of Otto cycles becomes 56.47.